before we start, we have to explain what encoding is. Basically, we all know that information that's stored and transmitted electrically and digitally is done as ones and zeros, right, in binary language. So if I want to send, let's say, a text, an image, or anything, first I have to represent it in binary. So we'll take a simple example where we have symbols, or A, B, C, and D, that we want to represent in binary. So the first step is we map them to words in the smallest field possible using the least amount of bits. We map each one into a different string. The problem with digital components is that they're not foolproof, and sometimes you have glitches, and zeros becomes 1, and 1 becomes 0. And so what's generally done is in the next stage, we move it to a larger field in such a way that each word is represented by one word by adding extra bit redundancy bits to it. And what we get is that there's a larger field where only specific words actually represent valid code words. And so, for instance, if we look at the words in red here, which represent valid code words, if I have the all zero word and one of them is changed to a 1, the person who gets the receiver can tell that this is not a valid code word and can either decide, send me the information again, or sometimes you can even decide that, okay, I can assume what was the correct word, and that's the word that was transmitted. Our goal is to improve detection of not only small faults, but in cases where you have a malicious attacker whose ability is so strong that he's able to change any word transmitted as he sees fit. And we're able to do this in systems where the information is distributed non-uniformly.
We use one as an example of a system with a non-uniformly distributed information. As we know, we're more likely to use some letters as opposed to others. Using a program called input log, which is used for writing analysis, we were able to obtain the distribution of all of these shows. As you can see over here, the down key is used about just over 20% of the time, while, for example, F6 is barely used at all. And this just emphasizes the need for an encoding like this. And this is the diagram of what we do. The user types in the letters. Those letters are then encoded using the process we just described. And the attacker can attack here and insert an error, changing what was broadcast. Now, it's important to note that although we use the keyboard, we can use the proposed solutions in any system with non-uniformly distributed information.
So a few more basic concepts that we have to deal with. The first one is error masking probability, which is the probability of one error getting masked. And what does that mean? It means that if for any given error that's detected, right, the probability that the combination of that error and the actual transmitted code word will result in another valid code word, in which case the receiver won't be able to tell that there was any error. There's 3 types of attacks, mainly. The first one is an attack which is always detected, which means that given that specific error, any valid code word that was transmitted will be able to detect that since the result will be a non-valid code word. Similarly, there are attacks that are always detected, and no matter which word you send, attacks are never detected, which means that any word that you send will be mapped to another valid code word. The third type of attack is an attack where it's detected with probability. What does that mean? It means that there are specific code words that when you combine them with the error, you get another valid code word, and there are ones which will result in a non-valid code word, and the receiver will then detect. The concept of a robust code is any code where the maximum error masking probability is smaller than 1, which means that every error is either always detected or detected with probability. And this is what we want to focus on. Basically, if we have even one error that's never detected, then a smart attacker will just use that error constantly, and we will never be able to detect when he corrupts our information. There's several types of robust codes, though not many, because they're pretty difficult to construct. One of them, and the one we use in our simulations, is the punctured qubit code, which was developed by Yaron Numer and Dr. Karen over here.
Before we continue, we had to define the type of attackers that were going to be attacking our system. So we defined two main attackers, where a blind attacker and a memory attacker. Given a set of information words and a set of code words, the blind attacker, he has prior knowledge of the probabilities of each information word and each code word. And his goal is to try to change the code word using an error such that it will be mapped to another code word that does not correspond to the original symbol. The memory-based attacker is very similar, but in this case, he has memory and he has the conditional probabilities. This is important because the probability of using the letter U, for example, is very high when you just look at the general probabilities. But when you take into account the fact that the previous letter was the letter Q, so the probability of the letter U being the next letter transmitted is much higher. In both cases, the attacker is going to choose to transmit the error that will give him the highest error maximum probability.
So there are several existing solutions to this type of problem. Mainly there's one which is random encoding. The only solution there is the algebraic manipulation detection codes, or AMD for short. And what they do is that part of the encoding process, they insert an element of randomness there, where the result is that the error masking probability is based solely on the degree of randomness. The larger the random code word that you insert, into it, the better results you're going to get. Another option is deterministic encoding, which is basically the robust codes that we mentioned before. And in addition to it, there's another method called the security-oriented state assignment, which was also developed here by Yerucham and Dr. Karen. And what they found is, remember the first stage we discussed was of encoding was the mapping of a symbol to an information word. And normally that's done randomly. What they found is that there are ways to do it, there are specific ways that you can do it, which will generally lower the error masking probability and produce better results. We try to combine both, and we developed a new type of encoding called level out encoding, where basically we took the randomness effect and added it to a first stage, and we split the encoding process into two. We created a mapping of symbols into a larger field of information words in such a way that the amount of words that correspond to a single symbol are directly proportional to the probability of the symbol. So symbols with high probability can be mapped to more information words. So the first phase we described here basically gets an input as a symbol, and that gives you a whole range of possible information words. Out of those information words, we randomly choose one to then move on to the second phase. We do this as in a very simple example. If I have just two symbols, right, A and B, and A is done, the probability is 75%, while B is 25. So I can move it to 4 words, where the first 3 all correlate to A, and the last one to B. And if I choose out of those 3 one randomly, I get that every one of the information words I have now has a 25% probability. So now what we've basically effectively done is we now have a uniform distribution. Now robust codes we know work fine with uniform distributions. So all we have to do in the second phase is take that information word, encode it using a robust encoding process, like we mentioned before, like the puncture cube code, and we get a robust code.
Here we can see the influence of the level out encoding process. This yellow graph, the solid line, represents the original distribution, while the dotted line represents what it would be if the distribution were uniform for this amount of code. As we can see, when we didn't modify anything, it's greatly different. However, when we added just one bit of level out redundancy, the distribution more closely resembles a uniform distribution. And as we add more and more redundancy bits to the level out process, we get almost completely uniform distribution. We then ran our simulations. These are the results of the blind attack. We can see here the unmodified PC code, where we didn't make any changes. And the 3 green graphs, those represent level out simulations with different amounts of redundancy bits. And we can see that our
finally, what we can show here is just for visual explanation, we ran the simulation of the same type on the text of Little Red Riding Hood. And what you see before you is that on the two left ones, we have, it's a blind attack using different encoding processes. The one on the left is an unmodified 100-qubit code. It's a little tough to see in the lighting, but the one on the right is using the level out process with the same total number of redundancy bits, and though you can't tell, it does almost twice as well. The two on the right are, again, bigram-based attacks, and over here you can see it a little better. Same type of encoding process. The one on the left is an unmodified code, and the one on the right is a level out and encoding using the same number of redundancy bits, and here you can clearly see that they did better. The red represents every time an attack went undetected. Every time, and the black is just the regular attacks. So to conclude, out of the different solutions we gave, AMD is still produces the best results. Mainly as two very important drawbacks. The one is it's very, very difficult to construct. It has serious constraints on how to create it. And the second is that the computation involved is very, very difficult and it requires a lot of overhead in both time and hardware. The deterministic encoding that we mentioned, as we can see in the graph, when the attacker succeeds 60% of the time, that's really just not effective enough in these types of systems. The level out process we suggested, we saw, while not quite as effective as the AMD code, it definitely gave very, very effective results, and it's much easier to design and it costs a lot less in both time and hardware.